Okay, here's another one, number 3. This time we want to center this one at 0. Okay, which means we need something in this form, a sub n x to the n. We need something in that form. That's what we're trying to find, and we're going to use the idea of the power series. Okay, well, first of all, and this is just one approach. It isn't the only approach. It's one approach. Okay, this is the one I chose to take. You could do it a couple ways. I'll explain that after we finish this one approach here. I'll show you how this works. Okay, now I'm gonna leave that x out in front because my idea. So it's equal to x times this quantity, and I reverse the signs in here and move that negative in front of the variable term here because I want to identify that now. And I can see this. I see an a equal to -1, and I see my r equal to x squared. So in my series now, I'll have x times this thing. I have a -1, that's the a, and I have the r to the n will look like this. You'll raise that to the n. Okay. So I just use this, put my a in and put my x, my r in as in place of x. So my r is actually x squared. Okay, so this thing, and by the way, notice that when I did that, this right here, the fact that r is this, tells me this, which is another way to say this. So that gives me my radius and my interval of convergence. So now this is the same thing as this, -1. And now the variable, remember, is n in this case for this sum, not x. So you can bring that x inside and write this as x to the 2n plus 1. Okay. And it's finished. This is done. This is our answer with this interval of convergence, which you could write it like this if you wanted to. Either way, or if you wanted to, you can write it like this. That's your I of C. Okay. Now, there's another way to do this. I'm just going to mention. I'm not going to do it, but I'm going to mention it to give you some ideas. You could write this like so, using partial fractions. And then all you'd have to do is come up with the right size, the right parameters a and b, and you would have two separate functions that could each be interpreted as a geometric series, so the sum of the geometric series, and then you could add them together. And the interval of convergence would be the intersection of the two intervals of convergence for each of these, whatever they would be. Okay, but you'd have to come up with the a and then join these two together, and you could do that. You could do all that work. You would end up with the same thing that we get here. Okay, you'd end up with this, and you'd have to show. You could show that work if you wanted to, but that's another approach to the same thing. A third approach is sort of a combination of these two. Would be to think, okay, so that would be a second approach. A third approach would be, okay, here's x over x minus 1 times 1 over x plus 1. Okay, now this is kind of a long drawn out process, and I wouldn't recommend it unless you didn't have a choice. But you could treat this kind of like I did here, 1 over x minus 1, and then times 1 over x plus 1. If you could come up with these the series for each of these using geometric series ideas the same way we did here, you then find the product of these, and you would be in business. But that would require expanding both of these. So you would have the product of 2 infinite series, and it's a term-by-term multiplication. A lot of work. Sometimes it is possibly the best way to do a problem, but in this case it would not be. But you could do it. You can find the infinite series for both of these, and this one, in fact, this isn't that hard to do, at least to line it up, not to actually do the work. I'm not going to do the work here. It's that times this. We'll write this as 1 over 1 minus a negative x, like that. So that each of these becomes, we'll have x, and then this will be times. And this one here, I put that negative up top. You know, you kind of can't see it there, but this first one, I'll initially do it like this, so you can see where it's coming from. You have this with a negative 1, and then you have an x to the n, like that. Okay, and then the other series looks like this. 0, and then you have a negative x to the n, like that. Okay, and then what you'd have to do is expand these. You'd have to do this. You'd have the first term. See, because these are sums, you can't just multiply the general terms together. Because this represents a sum, you'd actually have to do the long distributive work here. So the first term would be a negative. Of course, this negative, you could put that out in front over here. It's just going to mess you up with your multiplications. The first term would be a 1. Next term would be an x, and then an x squared, an x to the third, etc. And then this other series, this would alternate. This one would start off with a 1, and minus x plus x squared minus x to the third plus. Okay, so your job would be to find this product and start multiplying, distributing, and that would be a lot of work. You wouldn't have to do. You may do about maybe 4 multiplications to figure out what the patterns begins to look like, and then you'd probably be safe with about 4 or 5 multiplications, adding like terms and so forth. But it is a lot of work, and you would ultimately end up with the same thing we got here if you did everything exactly right. So that is another way to get an answer to find a power series. Now, if it's going to take that much work, then you might just say, you know what, I'm going to go back to my Taylor series coefficients and just find the Taylor series about 0. In other words, Maclaurin series, using my derivatives and my coefficients like that. And you would come up with a power series, and that would be good enough. Turns out it would be equivalent to the other one, even if it didn't look like it at first. You could show that it's the same. So all of these series expansions end up looking the same if it's expanded about the same number. All right, so